an interesting problem. And why it's interesting? Because it has a torque. Okay, so the previous example, there's no torque. This example has a torque. Okay, so we were asked again to find the principal stresses. Okay, we are asked to find the principal stresses and maximum shearing stress at point H. Okay, at point H. So element H is the point of interest. Again, if some of you are interested, not always. Okay, I mean, in the real world, you're not given element H. Okay, you have to decide where is the most critically stressed. Okay, all right. So that is our force. We have a 13 kilonewton force acting on the YZ plane. Okay, so the first thing we have to do is we have to construct our transformation, and we're going to follow the diagram. So this is our X. Now this is our Y. And then we have over here our Z. Okay. And you don't see in this question, or you don't see this. So the radius of the shaft or the structure is 30 millimeters. Okay, you don't see that, but I'm writing that as a question. So the first thing we do is we have to break down the forces, the 30 kilonewton, into two components. Okay, so we know that we have a one force coming down in this direction, and that is your Fy, and the other one is in this direction. This is your Fz. Okay. So we can use similar triangles, right? So we know that 125 over square root of 125 squared plus by 300 squared. So this is a geometry, right? So this will be equal to Fz divided by 13 kilonewton. All right. So probably you guys will have learned this from 2P before. So therefore Fz will be equal to 125 divided by 125, or divided by square root of 125 squared plus by 300 squared, close bracket, times by 13 power 3 is equal to 5,000. Or 5 times 10 to the power 3 Newton. Then for Fy is equal to 300. Okay, and then this is equal to 125 squared plus by 300 squared. This will be equal to Fy over 13 times 10 to the power 3. So your Fy will be equal to 300 divided by square root of 125 squared plus y300 squared plus bracket times by 13 power 3 is equal to 12,000. So 12 times 10 to the power 3. Okay, so we know that our Fy is 12 times 10 to the power 3, and our Fz is equal to our Fz equal to 5 times 10 to the power 3, and our Fy equal to 12 times 10 to the power 3. Okay, so now we have got them into our components. Then again, like how I've taught you is we're going to look at them in different views. Okay, so I'm going to look them in the y-x plane first. Okay, so I'm going to we're going to draw this. This is x. This is y. So we have I'm going to sketch this. Okay, so 300 by 150. Okay, so 300, and then 150. Okay, and then we have a force coming down. Right, so this is 12 times 10 to the power 3, and then we have force going this direction, which is 13 times 10 to the power 3, and then we have our element H. So at that view, this is our element H. Okay, that's our element H. So the next thing we do is we have to construct our neutral axis. Okay, the sketch position out. So that's our neutral axis relative to element H. Okay, so this is our neutral axis. For your homework later on, I'll post today, you always apply this technique. You'll never go wrong. Okay, so from here, we know that there is a Fy. Okay, we are aware there's an Fy. And Fy is equal to minus 12 times 10 to the power 3 Newton. And if we were to apply the formula, stress Y is equal to Fy divided by A, right? Element H will be in compressive mode. Negative means compressive. Okay. And then we're going to draw, this is our rotation in Z, right? So we are going to have a moment in the Z direction, and I'm going to call this direction positive. Okay. So moment in Z, right, is equal to 12 times 10 to the power 3, right? Now, because the force, the 12 kilonewton, right, is parallel to the neutral axis, right? The distance that we multiply is this distance over here. Okay, so that's the distance. So if you were to look at that, distance is equal to 0.15. Okay, so this is equal to multiplied by 0.15. So 12 power of 3 times 0.15 is equal to 1,800 Newton meter. Okay, and the direction will be in this way. So now you can sketch your moment vector, right? I'm going to sketch our moment vector. This is our mz. Head of the moment vector is compression. Tail end is tensile. So when we apply the formula, right, where stress Y is equal to mz over izz multiplied by a distance x, and we know that element H is on the right hand side of the neutral axis and is in compression due to the moment acting about the z-axis. Okay. Anything else to analyze? The answer is no, nothing else to analyze. Then we look at the next view. Okay, we look at the next view now. Okay, so I'm going to copy the same image so it's easier for me and also easier for you to view. So the next view that we are going to look at is we are going to look at the YZ plane. Okay, we are going to view this in a YZ plane now. Okay, so this is your Y and this is your Z. And then when you view this, it looks like this. This is just a sketch, okay? Some of you might say, Eugene, it's a very bad sketch. I totally agree with you. Okay. Then you have a so-called something center look like this. Right? Then we put in our element H. And then we put in our neutral axis. Then from here, we know that we have a force coming down here. This is our 12 times 10 to the power 3 Newton. And then we have a force going in this direction, right? And that is our 5 times 10 to the power 3. Okay. So the first thing that we can see from here, based on this analysis, we know that we are going to have, now, for this case, you can, because both of them are arrows, right? We have to analyze both, but we have completed analyzing the 12 kilonewton. It's not going to induce anything extra from what we got from the view from above. So you can say we are done with 12 kilonewton at this point of view. So now we know that we have our, I'm going to call it positive going to the right. We have our VZ, which is equal to 5 times 10 to the power 3. Okay, Newton. And because it's a shaft, so the shear stress is equal to VZ, right, over I XX QX divided by T, right? And we know that at point H is at the centroid, right? So the element H is going to be tau max, right? Because it's at the centroid. Okay, because if you look at how the shear stress is distributed at the centroid, where Vx is acting on, you have maximum shearing stress on element H. Okay. Now the next thing that we're going to look at is moment in the x direction. Okay. So moment in the x direction is equal to 5 times 10 to the power 3. So now the perpendicular distance is towards the element because the force is perpendicular to the neutral axis, right? So the measurement is take to the element, which is equal to 0.3 minus by 0.1. Okay, 5.3 and y.1. Okay, so this will be equal. So this will be equal to 5 power 3 times 0.2. The moment is 1000 or 1 times 10 to the power 3 Newton meter. I do apologize if I take this direction as positive. Okay. So when that's the case, moment in x is in this direction. So this is compression, this is tensile. But what you see over here, element, so if we apply the formula where stress y is equal to mx over ixx multiplied by y. Okay. And what we realize, hold on, is it multiplied by y? No, multiplied by z. I do apologize. Okay. And we realize that element H is equal to 0 because it's at the what? Neutral axis. Okay. It's equal to 0. So we don't need to be really worried about moment in x. Okay, then we are going to do another view. Okay, and rather than pasting another image, we are going to look at the so-called the plan view now. Okay, so I'm going to look at the XZ plane now. Okay, because you'll see something very unique on the XZ plane for this example. Okay, so this is our Z, this is our X, and this is rotation about Y. Okay,